Okay, in this video we're going to be talking about correlation. Okay, so we're going to be looking at the relationship between actually between paired data values, and they're going to be quantitative data values that we'll be looking at. Okay, so in this case here, let's start off with some of the basic concepts. And we'll give you a definition of what correlation is to begin with. Correlation is defined, correlation exists between two variables. And that's when the values of one variable are associated with values of the other variable. That's the basic definition of a correlation. It exists between two variables. So here, one variable has to be associated somehow with the values of the other variable. And then, a specific type of correlation would be a linear correlation. And a linear correlation, that correlation exists between the variables and that's when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. Okay. That's the basic definition of a linear correlation. Okay. It exists between the variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. And in this case, let's look at some illustrations of correlations. Okay, and here we can often see the relationship between two variables by constructing what they call a scatter plot. And this one on the left-hand side that you see represents a positive correlation. You can see that these data values, actually these paired points, the points of paired data usually increase as the x value increases. So that's a positive linear correlation. Now, the next one is a negative linear correlation. You can see, in this case, these data values or these points start declining. In other words, as your x values increase, the y value tends to decrease. And here, it's going to have a negative slope. Whereas with a positive correlation, it will have a positive slope. Okay, next is a graph where there is no correlation. Here the points are scattered everywhere in the XY plane, so there is no correlation. Now this next one right here, This one has a nonlinear relationship. It does have some type of relationship in this case, as you can see, but it's not in the form of a straight line. Okay? So that would be considered nonlinear relationship. Okay? And here's a summary of how we can interpret those plots. For a positive linear correlation, as your x values increase, the corresponding y values also increase. And a negative linear correlation is this: as the x values increase, the corresponding y values decrease. And of course, with no linear correlation, that means that there is no distinct pattern that exists in a nonlinear relationship. There is a distinct pattern, but it's not that of a straight line. Okay, so those are the 4 ways that we can interpret scatter plots. Okay, now the next definition I'm going to show you, I'm not going to write it down, but I'll let you see it on the screen. That definition is called a linear correlation coefficient, and that linear correlation coefficient will be denoted by the lowercase r. And what that linear correlation coefficient does, it measures the strength of the linear correlation between the paired quantitative x and y values in the sample. Okay? That linear correlation coefficient measures the strength of a linear relationship between the paired quantitative x and y values in that sample. And sometimes that linear correlation coefficient is often referred to as the Pearson product moment correlation coefficient. And that's named after Karl Pearson, who developed it originally. Okay. And we do calculate the linear correlation coefficient using our sample data. And it is a sample statistic used to measure the strength of the linear correlation between x and y. Okay, so in this case here, if we were to have every pair of x and y values from the entire population, then that means we will have a population parameter that's going to be represented by this Greek letter rho. It looks like the P here, but it is, in Greek letter, is the Greek letter rho. Okay. Now let me go ahead and introduce to you the test statistic for calculating a linear correlation coefficient, which is of course R. Now first of all, let me give you the requirements for calculating a linear correlation coefficient. Number 1, your sampled paired data, and that's x and y. It's a simple random sample of quantitative data. If you recall, quantitative data is nothing but numerical data. So, yeah, paired data, x and y, that's a simple random sample. Number 2, visual examination of the scatter plot must confirm that the points will approximate a straight line pattern. So also we'll be looking at how to construct a scatter plot, because that scatter plot can help us determine whether or not those points will approximate a straight line. And number 3, because results can strongly affect the presence of outliers, any outliers that you have must be removed if they are known to errors. And the effects of any outliers should be considered by calculating R with and without those outliers included. Okay, because if you recall, outliers are going to be those data values that are far away from the other data values in that set. And that paired XY data value, if it's an outlier, it can affect the value of R, which is your linear correlation coefficient. Now, this right here is the formula for calculating R. And we're just going to focus on this one right here. Now, I realize that is a more complicated, it looks complicated, but in this case here, N is your numbered or paired data, and this right here is the summation of the product of X and Y, because you have to be given a paired data values X and Y, minus the sum of all your x's times the sum of all your y's, and that's all divided by the square root of. Now here you get two square root symbols. The first one underneath the first radical will be n times the sum of all your x squares. You square your x's and then take its sum minus the square of each individual x value, and whatever that sum is, it's going to be squared, times another square root where you have n, which is the number of paired data, multiplied by the sum of all your y squares. You square all the y's and then take that sum minus the sum of all your y's. That means you take the sum of each individual y value and then square it. Now with that formula that you see here, it simplifies the manual calculations, but R can be usually calculated with either computer software or a calculator, which is what we're going to be using in this case, the TI-83 and 84 plus graphing calculator to calculate the linear correlation coefficient, which is R. Okay, and then next we'll talk about how to interpret R. Now, if you're going to be using computer software to interpret R, in this case we're using the graphing calculator, we look at our p-value. If that p-value computed from R is less than or equal to the significance level, you want to conclude that there is sufficient evidence to support a claim of a linear correlation. Otherwise, there is not sufficient evidence to support the claim of a linear correlation. Okay, so when we use the TI-83 or 84 plus calculator, we can get the p-value, and I will show you how that's done. And also, if we would use, and on here it says table A-6, what you're going to do here is consider critical values from table A-6 as being both positive and negative, and draw the graph. And to clear that up, this is what table A-6 looks like. And that's the critical values of the Pearson correlation coefficient, R. Here, n is the number of paired data, and you only get two alpha levels. One will be for 0.05 and the other one will be for 0.01. And that's all there is to it. Okay, and there's not much of this table because this goes only up to 100. Okay, so now, to determine if there is a linear correlation, you want to determine if the computed linear correlation coefficient lies in the left tail beyond the leftmost critical value, or if it lies in the right tail beyond the rightmost critical value. If that's the case, then you conclude that there is sufficient evidence to support the claim of a linear correlation. And no correlation would be this: if your computed linear correlation coefficient lies between the two critical values, then you conclude that there is not sufficient evidence to support the claim of a linear correlation. Now, with that, there is an equivalent criteria. And that's this. If the absolute value of R, which is this notation right here, exceeds the value in that Pearson correlation coefficient table, which is table A-6, you can conclude that there is a linear correlation. Otherwise, there's not sufficient evidence to support the conclusion of a linear correlation. Okay. So here we can use that to determine a linear correlation, sufficient evidence of a linear correlation, or no sufficient evidence of a linear correlation. Okay, now let's look at some of the properties of a linear correlation coefficient, which is R. The value of R is always going to be a number between -1 and 1 inclusive. That means R is going to be between -1 and +1. And that does include -1 and 1. And if all the values of either variable are converted to a different scale, then the value of R will not change. And the value of R is not affected by the choice of x and y. You can interchange all your x and y values and the value of R will still remain the same. Number 4, R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. Okay? You have to have a linear relationship to calculate R so you can measure that strength. And R is very sensitive to outliers in the sense that a single outlier can dramatically affect its value. Okay? Just like if you have an outlier in a set of numerical data values, that outlier can affect the mean or the average of the set of data. The same thing for the linear correlation coefficient R. Okay. And then the next thing we'll discuss is interpreting R, which is the explained variation. And that's this. The value of R squared. That's going to be the proportion of the variation in Y that is explained by the linear correlation coefficient or the linear relationship between X and Y. So once you find the linear correlation coefficient, you can just square that and get the explained variation. And there are some common errors that involve correlation. One of them is assuming that correlation implies causality. Okay? Okay. If there's a correlation between the two, we can't say that the first variable is the cause of the second variable, or the second variable is the cause of the first one. That's not true. Okay? And also data based on averages is also a common error. And also the property of linearity is another common error that involves correlation. Okay. Now, with the examples we're going to be doing is the ones where we have to apply the hypothesis test for correlation using the test statistic R. Okay, so in this case here, with the hypothesis test, I'm going to go ahead and bring up the null and alternative hypothesis, because basically the null and alternative hypothesis when you're dealing with correlation is quite simple. Okay? Now the requirements are the same for those given for determining a linear correlation between two variables. Okay, because we already talked about that a little bit earlier. Now, here's the setup of your null and your alternative hypothesis for a linear correlation. Your null is always going to be this: rho is equal to 0, meaning that there is no linear correlation. And your alternative will be rho is not equal to 0, meaning there is a linear correlation. Okay? You will not have to worry about the less than or the greater than in a linear correlation when you're doing hypothesis testing, because you're either going to have a linear correlation or you will not have a linear correlation between the two variables. And your test statistic, okay, is R, which is that formula that I already went over. However, you'll be using a calculator to calculate R. And then your critical values, we use table A-6, which is that Pearson correlation coefficient table for critical values. And again, the conclusion is this. Okay? And I think we talked about that already earlier. But here we can use the absolute value of R being greater than the critical value from that table. You reject the null and say that there is sufficient evidence to support the claim of a linear correlation. And if there is no correlation, which is where R, the absolute value of R, is less than or equal to the critical value, you fail to reject the null and say that there is not sufficient evidence to support the claim of a linear correlation. Okay. And then next we'll look at the p-value method. Now the p-value, we can easily use the graphing calculator to do that. Okay, it'll be much easier to use that graphing calculator to find that p-value of a linear correlation when we do the linear correlation coefficient. And the null and the alternative hypothesis are exactly the same, where the null is rho is equal to 0, meaning no linear correlation. The alternative is rho is not equal to 0, meaning that there is a linear correlation. Now the test statistic for that is going to be this formula. That's t is equal to r divided by the square root of 1 minus r squared over n minus 2. But in this case, your graphing calculator, your TI-83 or 84 plus calculator, will give you the test statistic, which is t. Not only that, it will also give you the p-value as well. And if we use that p-value approach, if you recall, if your p-value is less than or equal to your level of significance, which is your alpha level, you reject the null and say that there is sufficient evidence to support the claim of a linear correlation. Otherwise, you're going to fail to reject the null and say that there's not sufficient evidence to support the claim of a linear correlation. Okay. And at the bottom here, I'll summarize the hypothesis testing procedure for a correlation, which is similar to the 8-step procedure that we did for hypothesis testing for testing the claim about a proportion, the mean, and the standard deviation or variance. The first step, you state the original claim, and then next you state the opposite of the original claim, and then step number 3, identify the null and alternative hypothesis, and then step 4, state the level of significance. Step 5, compute the test statistic, which is R, which can be done using the calculator. Step number 6 is identify the critical value using table A-6. Now, you might have to identify the p-value as well. So step number 6 can have either the critical value or the p-value. Then step number 7 is your decision rule. Now, this only deals with the critical value, but if you use the p-value approach, then you compare the p-value with your level of significance to reject the null or fail to reject the null. And then write your conclusion using simple, non-technical terms. Okay. Now, let's look at this first example. I'll move this out the way. And we're going to start with a simple one right here. For a sample of 8 bears, researchers measured the distances around the bear's chest and weighed the bears. Minitab was used to find that the value of the linear correlation coefficient is R is equal to 0.751. Using alpha is equal to 0.05, that's your level of significance, determine if there is a linear correlation between chest size and weight. What proportion of the variation in weight can be explained by the linear relationship between weight and chest size? So this is split up in parts A and B. And in this case, part A is going to be that 8-step procedure. So here's step 1 is stating the original claim in symbolic form. Okay. Here we want to determine if there is a linear correlation between chest size and weight. So the original claim is going to be rho is not equal to 0, which means that there is a linear correlation between the two variables, weight and chest size. Step number 2 is the opposite of the original claim. Well, the opposite of not equal to is equal to, so it will be rho is equal to 0, meaning that there is no linear correlation between the two. And then from there we can write our null and alternative hypothesis. That's easy because the null always has the equal sign. The alternative does not. It has the not equal to. Okay? So that's your null and your alternative hypothesis. And then step number 4 is stating your level of significance, which means alpha is equal to 0.05. Okay, so alpha equals 0.05 is your level of significance. That's given to you in the problem. Okay, now step number 5 is also easy as well, because that's given as well. Usually we calculate your test statistic, but in this case, your linear correlation coefficient is your test statistic, which is in this case R, and that's equal to 0.751. Okay, now step number 6. What I'm going to use is the critical value approach. What I mean by that is this. There were 8 bears for that sample, N is 8, and the alpha level was 0.05. So this is where I use this table of the critical values of the Pearson correlation coefficient. So here, N is 8, and the alpha level is 0.05. So I look in this column where alpha is 0.05 and N is 8. That's going to be my critical value here, 0.707. So in this case here, the critical value is equal to 0.707. Right, now step number 7. Since we're using the critical value approach, this will be our decision rule. If the absolute value of R is greater than the critical value that we found, you're going to reject the null. Okay. Now going back to step number 5, we found out that R was 0.751. So if you take the absolute value, it's going to be positive. So the absolute value of 0.751 would be 0.751. Now you're going to compare that with the critical value of 0.707. Now if you compare those two, you'll see that 0.751 is greater than 0.707. So here we can reject the null hypothesis. So here we're rejecting the null, and the claim was the alternative hypothesis anyway, so our conclusion would be this. There is sufficient evidence of a linear correlation between chest size and weight. Okay, that's our conclusion here. Okay, now this one is quite simple because we already know what the linear correlation coefficient was that was given to us in the problem. Okay, since we didn't have any sample data that was given, we had to use the critical value approach to compare that linear correlation coefficient with the critical value. Now part B, what proportion of variation in weight can be explained by the linear relationship between weight and chest size? Alright, back to step 5, it says R is equal to 0.751. So the proportion of the variation is simply R squared. So here we just take that R, which is 0.751, and square that. And that will give you 0.564. Okay. So that 0.564 represents the proportion of variation in weight that can be explained by the linear relationship between weight, and chest size. Okay, now let's look at another one that's very, very simple. In this case here, the heights in inches and pulse rates in beats per minute for a sample of 16 women were measured. Using technology with the paired height pulse data, the linear correlation coefficient is found to be 0.431. Is there sufficient evidence to support the claim that there is a linear correlation between the heights and pulse rates of women? So here you want to use the significance level of alpha is equal to 0.05. Now again, we can apply that 8-step procedure for hypothesis testing. So starting with step number 1, we want to state the original claim. And the claim is that there is a linear correlation between the heights and pulse rates of women. So that means rho is not equal to 0, meaning that there is a linear correlation. Then step number 2 is the opposite of the claim. That would be rho is equal to 0, meaning that there is no linear correlation between the two. And then step number 3, we can write our null and alternative hypothesis. Of course, the null always has the equal sign in it. So that means that your alternative will have the not equal sign, because the alternative has either not equal to or greater than or less than. Okay, and then step number 4, stating your level of significance. In this case, we're using a 0.05 level of significance, so alpha is equal to 0.05. Okay, and then step number 5 is our linear correlation coefficient, which is R. Now again, just like in the last example, they give you the linear correlation coefficient, which is your R, 0.431. So in this case here, R is equal to 0.431. Okay, now for you to use that formula, you have to be given sample data. In this case, you're already given the linear correlation coefficient. Now step number 6 is we're going to have to use the critical value method because we don't have the sample data. Okay, we do know we have 16 women, N is 16, and our alpha level is 0.05. So we can use that table A-6 or the Pearson correlation coefficient table. We're looking in this column for the 0.05, and we're going to find 16. And in this case, that's what, 0.497. So that critical value for 16 data values at the 0.05 level of significance is 0.497. Step number 7 is finding using your decision rule. And that's this. If the absolute value of R, we're using a critical value approach, so the decision rule is this: if the absolute value of R is greater than your critical value, you're going to reject the null. So the absolute value of 0.431 is 0.431. We're going to compare that to the critical value of 0.497. And comparing these two, 0.431 is less than 0.497. Unfortunately, it does not satisfy our decision rule, so that means that we fail to reject the null hypothesis. we fail to reject the null hypothesis. And then we write our conclusion using simple non-technical terms. So in this case here, we say that there is not sufficient evidence. There is not sufficient evidence that there is a linear correlation between the heights and pulse rates of women. Okay, so that's your conclusion statement there, using simple non-technical terms here. Okay, and that's how we apply that 8-step procedure to this particular problem, which was quite easy. Okay, but now we're going to look at another example that has the sample paired data. And this is where we're going to apply the use of the graphing calculator to get the linear correlation coefficient of R. Okay, so here before I do that, I've also included this, the procedure for using a TI-83 or 84 plus calculator to construct a scatter diagram or a scatter plot. Now here you're going to enter or open two lists of data with the corresponding entries paired. And then you're going to select stat and then plot, and that's the function by pressing second and then y equal for stat plot, and then enter and use the arrow keys to turn on plot 1 to the on state, and also highlight the graph type shown in the third line of the display. Then press zoom 9 to obtain the scatter plot. Okay. Now, I do have the procedure for doing the correlation with paired data. Now you have to store your paired data in L1 and L2. Okay. Now number one, you'll enter or open the two lists that contains that paired sample data. And then you're going to press the stat key and then press the right arrow button to select the item that says test. And then proceed to select the menu item of lin-reg t-test. That's short for linear regression t-test. And for the X list, you'll select L1. That's for the first variable. And then for the Y list, it'll be L2 for the second variable. The frequency will always be 1. And then for the row that's labeled beta and row, you're going to select the option of, in this case, not equal to 0. Because that's the choice to test the null hypothesis where rho is equal to 0. Okay? And that's determining whether there is a linear relationship between the two variables. Then you'll scroll down to calculate and then press the enter key. Okay? Now, you might have to press the down arrow key to scroll down for additional results, because you're going to have too many results to fit all of it on that one screen. Okay, so that's the procedure here. Now, let's take that and apply it to this problem here. Listed below are annual data for various years. The data are weights in metric tons of imported lemons and car crash fatality rates per 100,000 population. Construct a scatter plot and find the value of the linear correlation coefficient, which is your R, and find the p-value using alpha is equal to 0.05. Is there sufficient evidence to conclude that there is a linear correlation between lemon imports and crash fatality rates? Do the results suggest that imported lemons cause car fatalities. And this is the data set that we have. And these are paired data, lemon imports and crash fatality rates. So here we're going to construct the scatter plot. So and I'm probably going to have to move this up so you can just see the table. And then here's the screen for the calculator. Now in this case, what we're going to do is select stat plot by pressing the second key and Y equal. Okay? And I'll move this up here second, which is this blue key or the yellow key, and then Y equal is the key on the left hand side next to the screen, and it's right below the screen. You have 5 screens. The first screen is Y equal. You'll select that after pressing second and then Y equal. Now you should get this menu. Now actually, before we get to that, we need to enter this data into the into tables L1 and L2. So let's press this stat key right here. Press stat, and then we're going to edit. So we're going to select number 1 for edit. Now I have a lot of data values here, so what I'm going to do is erase all of this by doing this. For L1, to erase those data values in L1, you hit your up arrow key and then press clear and then enter. Okay, again, I have data values in L2, so I'm going to hit my up arrow key to highlight L2, press clear and enter. And I'm going to do the same thing for L3. Hit my up arrow key, press clear and enter. Okay, now I can enter those data values here. Now L1 is going to be the lemon imports. That top row is the lemon imports, so we'll enter those data values here, and that's 228, 265, 359, 482, 531. And then hit your right arrow key to go to L2, and then type in the crash fatality rates. For 228 is 15.9. Oops. That should be 0.9. And then 15.6. And then 15.4, 15.3, and 14.9. Now, the same number of data values in L1 must be the same number of data values in L2, because these are paired data. So you must have 5x values in L1 and 5y values in L2. Okay, now we go ahead and press second and Y equal to. And then I'm going to select number 1. Now in this case here, I see that my plot is off. So to turn it on, I place the cursor on the on command and press enter to turn it on. Okay. Now, the one I'm going to select is, now it says the graph on the third line of the display, but in this case right here for the type, I would select this first one right here, as you see. That's highlighted. I'll select that one and then press enter. And then my X list will be L1. That stays the same. L2 will be the Y list. And then the mark, you have 3 choices here. I'm going to pick this first one right here. Okay? And then after that, we're going to go ahead and press zoom, which is the third key, the third button on this top row below the screen, and then select number 9 to obtain the scatter plot. And here, this is what the scatter plot looks like. Here you can see those dots are declining. So here, I would assume that it's going to have a negative linear correlation. And on the homework, you'll be given a choice of scatter plots to choose from. So you have to choose the one that looks closest to this that's on your calculator screen. Okay, so that's your construction of your scatter plot. Now we want to do our hypothesis test. Okay, because we want to find the value of the linear correlation coefficient and find the p-value using alpha is equal to 0.05 to determine if there's a linear correlation between lemon imports and crash fatality rates. Okay, so let's start off with that 8-step procedure. In step number 1, you want to state the original claim. And you're determining if there's a linear correlation between the two. So it'll be rho is not equal to 0. That's your original claim. Then step number 2 is the opposite of the original claim. Well, the opposite of not equal to is just plain equal to. So that means that rho is equal to 0, meaning that there is no linear correlation. Whereas rho is not equal to 0 means that there is a linear correlation. Then step number 3 is writing the null and alternative hypothesis. In this case here, the null is the one that has your equal sign in it, rho is equal to 0, and the alternative would be rho is not equal to 0. Then step number 4 is our alpha level, or level of significance, which is in this case 0.05. Okay. Now I'm going to put step 5 over here. So here's how we do step number 5. Okay, so I'm going to bring back the graphing calculator here. Now those data values have already been placed in L1 and L2. So the next thing I'm going to do here is press the button that says Stat. Here's the Stat button right here. Press that button, and I'm going to use my right arrow key to highlight the menu item the menu that says Test. Okay. Now I'm going to use my down arrow key to find the menu item under Test that says Lin Reg T-Test. So we keep pressing the down arrow key until we find it. Here it is. Lin Reg T-Test. That's the linear regression T-Test. Okay? Then we press enter. Now, the X list is L1, so we leave that as is. Your Y list will be L2, so we leave that as is. The frequency is 1, so we leave that as is. But here we look at our alternative hypothesis, which is rho is not equal to 0. So under this line where it says beta and rho, we want to put the cursor on top of the not equal to 0 item and then press enter, because we're always testing that there is a linear correlation between the two. So we always use the not equal to 0. We're never going to use less than 0 or greater than 0. And then hit your down arrow key to go down to calculate. And then press enter. Okay. Now, as you can see here, there's an arrow on the far left hand side. That means that there is more information to this. So, press your down arrow key, because that's going to give us the linear correlation coefficient, which is your R. So here R, if we were to round that off to 3 decimal places, it would be negative 0.941. That R is your linear correlation coefficient, which is negative 0.941. Now they might ask for the T value, or your T-test statistic. Okay, and I can show you how to do that as well. If you scroll back up, okay, let me do this again, stat, and then test. Okay, now, usually you'll scroll back up to get the t-value. If you look right here, that lowercase t, that's your critical t-value as well. That's going to be negative 4.82829. Okay, so your t-value is negative 4.829. So sometimes they may ask for that critical t-value as well. And for r, that's your linear correlation coefficient, which is negative 0.941. Okay, step number 6. We're going to find the p-value, because the directions does say find the p-value. So in this case here, I can show you where the p-value here is located on the calculator. Right under the t is a lowercase p. That's your p-value. This decimal value is your p-value, which is, to 3 decimal places, 0.017. Okay, so that p-value is 0.017. Okay, you can see that it's much easier to use the calculator than using the that nasty and obnoxious formula, which can be quite confusing. And in the notes that I have, which I've done in the past, you can see the long way that I've done it. And then step number 7 is your decision rule. Since we're using a p-value approach, it'll be better to base our decision on the p-value and the level of significance. If your p-value is less than or equal to alpha, reject the null hypothesis. Now that p-value is 0.017. Your alpha level is 0.05. Well, in this case, 0.017 is less than 0.05. So here, that satisfies the decision rule, so we can reject the null hypothesis. And if we reject the null hypothesis, that means that there is sufficient evidence of a linear correlation. So our concluding statement is this: that there is sufficient evidence of a linear correlation between lemon imports and crash fatality rates. Okay. Okay, so that's our conclusion statement right there. And that's how we do a linear correlation coefficient. Sometimes they may ask for R and for T. So pay close attention to the homework. So it's important that you do use that graphing calculator to help you get the R and the T value, and also the P value as well. Okay, one last example is this. Let's say listed below are the overhead widths in centimeters of seals measured from photographs and the weights in kilograms of the seals. Construct a scatter plot and find the value of the linear correlation coefficient, which is R, and find the critical value of R using alpha is equal to 0.05. It's very important to find the critical value. Is there sufficient evidence to conclude that there is a linear correlation between overhead widths of seals from photographs and the weights of the seals? So this is our table relating X be the overhead width, and the Y be the weight. Okay, so in this case here, we'll go ahead and put this in our table here. This will be L1 for the overhead width. The weight will be in L2. Okay, so using my calculator, press the Stat key, and then we're going to edit. Now we got data values in L1 and L2, so I'm going to use my up arrow key to highlight L1, press clear and enter, right arrow over to the L2 column, highlight the L2, using the up arrow key, press clear and enter. Now in L1 I'm going to put the data values for the overhead width. So 7.2, 7.5, 9.8, 9.4, 8.7, and 8.4. And you have to make sure that you press enter after each individual data value, especially the last one. Then use your right arrow key to put the data values of your weight in L2. 118, 165, 246, 203, 200, 191. And then hit enter. Because you have to have the same number of data values in L1 as you do in L2. And 7.2 has to be paired with 118. 7.5 is paired with 165, and so on, because these are paired data values. Now for the scatter plot, press second and Y equal for your scatter plot. Now, we see that plot 1 is already on, so I'll select number 1 for your plot 1. Okay, and for the type, I will leave it as this first one right here that's highlighted. L1 will be in the X list, Y list will be L2, and I'll leave this mark the same. You can change it if you want to. And after that, press zoom and 9. And that's what your data values look like. Okay. And by the way, some people might not know what zoom 9 is. Let me go back to zoom. Hit your down arrow key to number 9. Oops. Zoom 9 means zoom stat. Yeah. Zoom 9 means zoom stat. So it's your plotted data points will look like this. Okay, and here we have a positive correlation, I would assume, because as the X values increase, your data values are increasing as well. Okay, so that's your scatter plot, and you'll be given a choice of answers of scatter plots to choose from that would look. You have to choose the one that would look similar to the ones that's on your screen. Okay, now let's do the hypothesis testing procedure, because you got to find the linear correlation coefficient of this set of data values, set of paired data. Step 1 is your original claim. Okay, we're trying to conclude that if there is a linear correlation between the two variables, that means rho is not equal to 0, meaning that there is a linear correlation between overhead width and weight. Step number 2 is the opposite of the original claim, which means rho is equal to 0, meaning that there is no linear correlation between the two. And then step number 3 is stating our null and the alternative hypothesis from steps 1 and 2. Well, the null has the equal sign in it, so we say rho is equal to 0, and then the alternative hypothesis will be rho is not equal to 0. And then step number 4 is our alpha level, which is 0.05, that was given to us in the problem. Okay, then step number 5 is calculating that linear correlation coefficient R. Okay. And in this case, we only want just R. Now, our data values have already been entered into the calculator, so what we'll do here from there is just press the Stat key. Hit your right arrow button to highlight the test menu. Hit your down arrow key to find Lin Reg T-Test, which is linear regression T-Test. And that's this menu item right here under Tests. And then press Enter. X-list is your L1, that stays the same. Your Y-list is L2, that stays the same. Frequency, that's your 1, that stays the same. You want to highlight the not equal to 0 because your alternative hypothesis is rho is not equal to 0. And then you hit your down arrow to the calculate item, highlight that, then press Enter. Now we want to find just R, so we hit our down arrow key because that tells us that there's more information to it. So your R, in this case the 3 decimal places will be 0.935. So here R is 0.935. Okay. Now we're not worried about the p-value because they're asking for the critical value, because they want you to find the critical value of R using alpha is equal to 0.05. So this is where step number 6 comes in. We have, in this case, there are 6 paired data. That N represents the number of paired data. And our alpha level was 0.05. So this is where we use that Pearson correlation coefficient table to find the critical value. Here we got 6 paired data, and the alpha level is the 0.05. That's the first column, so that critical value is 0.811. So that critical value for 6 paired data at the 0.05 level of significance is 0.811. Now step number 8. Since we're using a critical value method, we must use the decision rule for a critical value for comparing the critical value and the linear correlation coefficient. And that's this. If the absolute value of R is greater than your critical value, you reject the null. So now if you compare, the absolute value of 0.935 is 0.935, and then your critical value was 0.811. Compare those two, 0.935 is greater than 0.811. And because it does satisfy the decision rule, we can reject the null hypothesis. Okay, and then step number 8 will be just simply writing our conclusion statement. Because we reject the null hypothesis, that means that there is sufficient evidence to conclude that there is a linear correlation between overhead widths of seals from photographs and the weights of the seals. Okay. All right. So in this case here, that's your hypothesis testing procedure, and also the doing of a scatter plot, which can be done on the TI-83 or 84 plus calculator. So here, that type of technology, and also you do have StatDisk that's also available for you to use to find the linear correlation coefficient and other things as well. Okay, so that is going to conclude this particular video on correlation.